In this video, we're going to take a look at some examples using integration by substitution. We recall that the substitution rule for indefinite integrals says that as long as f of x is a continuous function, then the integral of f of g of x times g prime of x dx can be written as the integral of the function f of u du by making the substitution u equals g of x. And so the idea here is to let u equal the inside function of our composition, and then du would represent the derivative of that function. In this example, we want to evaluate the indefinite integral of t squared times the square root of t cubed plus 12 dt. We recognize that we have a composition of two functions in the integrand here. We have the square root of t cubed plus 12. And so we're going to let u be the inside function of that composition, which is t cubed plus 12. Once we have u, we can find its derivative du. That would be 3t squared dt. Now we have a bit of a problem. When we go to substitute everything in, we see that we can certainly substitute u inside the square root, but we don't have du here. We only have t squared dt. So we only have part of our expression for du. We're missing a constant of 3. So one way we can adjust for this is to take this equation for du and divide both sides by 3. And when we do that, we get that du over 3 is equal to t squared dt. And now t squared dt is exactly what we have to substitute in. And so instead of substituting in just du for that leftover expression outside the square root, we're going to substitute in du over 3. And so here, when we do that, we're going to be getting the integral of the square root of u times du over 3. And now we want to compute this integral. To do that, we can bring the constant 1/3 outside the integral, and we can rewrite the square root of u to have the form u to the 1/2. And u to the 1/2 du, that is an integral of a power function. So we can use the power rule like normal. So this will be u, and we add 1 to the exponent to get 3/2, and then we divide by that exponent, so divide by 3/2, and of course plus c. And so we end up with 1/3. Instead of dividing by 3/2, we can think of that as multiplying by 2/3, u to the 3/2 plus c. And at the end, we can combine our constants to give us a constant of 2/9. And then u we can replace with t cubed plus 12. So we have t cubed plus 12 to the 3/2 power plus c. And so the final form of our indefinite integral is 2/9 t cubed plus 12 raised to the 3/2 power plus c. Notice here that when we did our initial substitution, it was crucial that we accounted for that missing factor of 3 in the du expression. As long as we're only missing a constant like we are here, the integrand here is missing the constant 3, we can always adjust in a similar fashion by dividing the du equation by that constant and substituting in the expression du over that constant. Again, in this case, du over 3. So whenever we're missing just a constant from our du term, we can make this adjustment, and the substitution and integration should work out just fine. If you'd like to try a similar example, pause the video and try to evaluate the integral of x to the 5th times x to the 6th minus 3 to the 12th power dx. Resume the video, and in a few seconds, you'll see the worked out solution and final answer for this problem. Here we're going to let u equal x to the 6th minus 3, the inside function of our composition. Du will then be 6x to the 5th dx. Du over 6 is x to the 5th dx, and that is what we need to substitute in since the integrand there is missing that constant of 6. And so we substitute u and du over 6 into our integral to get the integral of u to the 12th times du over 6. We can factor out the 1/6 outside the integral. The antiderivative of u to the 12th is u to the 13th over 13. And combining the constants and substituting x to the 6th minus 3 in for u results in the value 1 over 78 times x to the 6th minus 3 to the 13th power plus c. In this example, we want to evaluate the integral of sine of t over cosine to the 7th of t. We notice here in the denominator, we have cosine to the 7th power of t, which means we have cosine of t being raised to the 7th power in that denominator. This means that our inside function of our composition is going to be the function cosine of t. And so that's going to be the value for u in this substitution. So if u is cosine of t, du must be the derivative of that, which we know is negative sine of t dt. Now we notice here that we have a sine of t dt, but we're missing the negative. And so here we can rewrite this as negative du as sine of t dt. And now we're ready to go with our substitution. We have in our numerator a negative du, and that will take care of the sine of t and the dt. And in the denominator, we have u to the 7th power. So we have an integral of negative du over u to the 7th, which we can think of as negative of the integral u to the negative 7th du. So we can evaluate this integral using the power rule. So we get u to the negative 6 power divided by negative 6, all plus c. Of course, the negatives here will cancel. And so we just get u to the negative 6 over positive 6, or 1 over 6 u to the 6 plus c by moving the u to the negative 6 to the denominator, which makes our exponent positive. And our last step is to go back to our original variable t. So we obtain 1 over 6 cosine to the 6th of t, all plus c. So this is our antiderivative for the function sine of t over cosine to the 7th of t. If you'd like to try a similar example, pause the video and try to evaluate the integral of natural log w to the 8th power all over w dw. Resume the video, and after a few seconds, you'll see the full solution. So here we let u be the inside function of our composition, the natural log of w. Du is the derivative of the natural log of w, which is 1 over w dw. We substitute u and du into our integral to obtain the integral of u to the 8th du. The antiderivative of u to the 8th is u to the 9th over 9. And substituting back to our original variable of w, we find that the integral is equal to the natural log w to the 9th power all over 9 plus our arbitrary constant c. In this example, we want to evaluate the integral x times x minus 2 to the 100th power dx. When we look at the integrand of our integral, we notice that we have a composition of functions, the x minus 2 to the 100th power. So by the convention for substitution, we're going to let u be the inside function of that composition, which will be x minus 2. Once we choose u, we know du will be the derivative of that, and the derivative of x minus 2 is simply dx, or 1 times dx. This then gives us somewhat of a problem when we go to substitute in, because we have this factor of x sitting out front in the integral. We're able to substitute in the u for x minus 2 and du for dx, but when we do this, we're going to be left over with a factor of x, and having two variables in the integral is not going to be useful. And so what we're going to do in this case is look at our substitution that we made for u, where here we had u being x minus 2. And notice that if I add 2 to both sides of this equation, we get that u plus 2 is equal to x. And so this can then be substituted in for that extra factor of x that we have in our integral. So now we have everything that we need to substitute into our integral to get an integral in just one variable. So if we substitute everything in, we're going to substitute in u plus 2 for x, that first term. For x minus 2 to the 100, we're going to substitute u in for x minus 2 to get u to the 100. And then for dx, we're going to substitute in du. And now we have an integral totally in terms of u, and there's no x's in sight. And so this is a relatively easy one to compute. To actually evaluate it, we are going to distribute the u to the 100. So we have u times u to the 100, which is u to the 101, plus 2 times u to the 100, all du. And now we use the power rule in each term. So this will give us u to the 102nd power over 102, plus 2 times u to the 101st power over 101, plus c. And our last step, as always with substitution, is to go back to the original variable. So in this case, we replace u with x minus 2. So we have x minus 2 to the 102nd power over 102, plus 2 times the quantity x minus 2 to the 101st power over 101, plus c. And this final expression is our indefinite integral of x times x minus 2 to the 100 dx. If you'd like to try a similar example, pause the video and evaluate the integral of z over z minus 1 dz. The solution will appear in just a few seconds. For this example, we'll let u equal the denominator, z minus 1, so that du is equal to dz, which is the derivative of z minus 1. Since we also have a factor of z in the numerator, we're going to solve u equals z minus 1 for z by adding 1 to both sides, and we'll get u plus 1 is equal to z. And then we'll substitute that expression into the numerator. And so we have the integral of the numerator, u plus 1, divided by z minus 1, which is u, times du. U plus 1 over u, we can rewrite as a sum, each of those terms in the numerator over u. So we have u over u, which is 1, plus 1 over u. And we can integrate each term independently. So the antiderivative of 1 is simply u. And the antiderivative of 1 over u is the natural log of the absolute value of u. And of course, plus c. Now recall here that when we do evaluate 1 over u in terms of an antiderivative, we do have the absolute value bars here. And that's because the natural log is only defined when the thing we're taking the natural log of is positive. And here we're not guaranteed that u, or later z minus 1 in the next step, will be positive. That might be a negative number. And so we always need to include the absolute value bars when we use an absolute value involving an antiderivative involving natural log, like this one. And so the last step here, we go back to the variable z, replacing u with z minus 1, and the natural log of u with the natural log of z minus 1, of course, plus c.